Santorini is a world-famous island paradise, known for sunset views, white villages, and clear blue water. But beneath the Mediterranean Sea, a long-hidden geological mystery has suddenly moved. In early 2025, more than 28,000 earthquakes rattled this peaceful region, forcing authorities to declare a state of emergency. When scientists examined what was happening beneath the seabed, they did not find an ordinary sequence of shifting faults. Instead, they discovered a pulsing, wave-like mass of liquid rock tunneling between two ancient volcanic giants. This is the story of a hidden underground highway, a shared volcanic heart, and an ancient structural blueprint that guided magma through the darkness beneath the Aegean Sea.
On a quiet afternoon in late January 2025, the postcard-perfect cliffs of Santorini began to shudder. At first, it was barely a whisper, a subtle but persistent vibration detected only by the most sensitive instruments on the island. Within days, that whisper became a roar. The earth began shaking several times every hour and sometimes every few minutes, jolting the whitewashed villages of Fyra and Oia. Along the steep volcanic cliffs surrounding Santorini's famous caldera, small rock slides tumbled into the sea. Concern quickly spread through the local communities, and the Greek government was forced to take emergency action. A state of emergency was declared across the island. Schools were closed, while tourists and residents began leaving by ferry and plane. Out of Santorini's population of approximately 15,500 people, more than 13,000 reportedly left the island within a matter of weeks. The normally crowded streets became eerily quiet. For generations, Santorini had been viewed as an isolated geological wonder, a dramatic half-moon-shaped island created by the collapse of an ancient volcano. But as seismologists examined the enormous volume of data coming from the surrounding sea, they realized that something much larger was unfolding. Deep beneath the dark waters of the southern Aegean, a hidden geological process was underway. Between late January and early March 2025, seismic instruments across the islands recorded more than 28,000 individual earthquakes in only 8 weeks. Hundreds of these tremors were strong enough to be felt across the region, while the largest reached magnitudes above 5. But when scientists studied the signals, they noticed a strange pattern. This was not a normal tectonic earthquake sequence, in which one powerful shock is followed by smaller aftershocks that gradually decrease over time. Instead, the earthquakes were migrating. Their epicenters, the points on the surface directly above the underground fractures, moved forward like a slowly advancing line. The sequence began west of Santorini at a depth of approximately 18 kilometers. It then traveled northeastward through a narrow corridor extending almost 30 kilometers toward a dark, submerged volcanic peak hidden beneath the waves. Scientists had discovered a massive underground intrusion of magma. It was a vertical sheet of molten rock, known as a volcanic dike, forcing its way horizontally through the Earth's crust. This liquid corridor contained enough magma to fill approximately 200,000 Olympic-sized swimming pools. It was actively breaking through solid rock and carving a new pathway beneath the sea. But why was the magma following this particular route? Where was it going? And what was it trying to reach? The search for answers led researchers toward an ancient geological blueprint hidden beneath the Aegean Sea. It also raised serious questions about the safety of the modern communities living on the fragile volcanic crust above. For decades, scientists worked with a widely accepted and seemingly reassuring belief. They thought the active volcanoes of the southern Aegean Sea were independent systems, isolated from one another by many kilometers of cold, rigid continental crust. Santorini, with its spectacular caldera and history of enormous, civilization-changing eruptions, was monitored as a separate volcanic structure. Its underground plumbing system was believed to consist of several stacked magma chambers positioned almost directly beneath the island. Approximately 7 kilometers northeast of Santorini lies another active volcanic giant. Its name is Columbbo. Columbbo is a submarine volcano whose crater rim reaches to within only 18 meters of the sea surface. It is the largest volcano in a chain of submarine cones stretching along a major fault zone. Columbbo produces explosive, gas-rich, rhyolitic magma. Santorini's historical eruptions, however, have produced a broader range of magma, including dacitic and basaltic lava. Because of these chemical differences, geochemists concluded that the two volcanoes must be supplied by completely separate and unconnected underground plumbing systems. Analyses of isotopes and trace elements in lava from the two volcanoes appeared to support this conclusion. The chemical fingerprints of Santorini's and Columbbo's magma suggested that they came from separate mantle sources. These sources appeared to operate under different conditions of temperature and pressure deep inside the Earth. Geologists therefore produced simple diagrams showing isolated vertical conduits rising from the mantle into separate shallow magma chambers beneath each volcano. There was no horizontal connection between them. This belief influenced the way the two volcanoes were monitored. If Santorini showed signs of unrest, scientists assumed that only the immediate surroundings of its caldera were threatened. If Columbbo experienced a small earthquake swarm, the activity was treated as a local event with little relevance to the tourists standing on Santorini's cliffs. The volcanoes were treated like polite neighbors who never shared the same source of fuel. But nature rarely follows the simple models created by human beings. Below the beautiful islands and deep basins of the Aegean Sea, the Earth's crust is under constant tension. The African plate is continuously moving beneath the Eurasian plate and sinking into the hot mantle below. This geological process is known as subduction. As one plate moves beneath another, the crust above is stretched and fractured, producing enormous zones of weakness, known as extensional faults. The old model overlooked an important reality. The deep crust is not an unbroken or impenetrable wall. It is a dynamic and heavily fractured environment in which tectonic stress and magmatic pressure are constantly competing for space. By early 2025, the stage had been prepared for a dramatic demonstration of this geological truth. The volcanic and tectonic crisis of 2025 shattered the old scientific consensus within a matter of weeks. For the first time, scientists obtained real-time geodetic and seismological evidence of a connected volcanic system beneath Santorini and Columbbo. To understand the exact structure of the crisis, an international team of scientists mobilized an extraordinary collection of advanced geophysical instruments. They combined traditional monitoring techniques with artificial intelligence, transforming thousands of underground vibrations into a detailed, three-dimensional picture of magma in motion. The first major line of evidence came from space. Satellites from the Sentinel. One mission used a technique called synthetic aperture radar interferometry, commonly known as NSAR. This method allowed scientists to measure changes in the shape of the ground with millimeter-scale precision. By comparing radar images taken before and during the crisis, researchers discovered a remarkable pattern of deformation. Santorini's caldera had been gradually inflating since the middle of 2024. But during the crisis, it suddenly began to subside and sink. At almost the same time, instruments positioned on the seafloor around Columbbo recorded another major change. The seabed inside Columbbo's crater sank by as much as 32 centimeters. How could one volcanic area sink while another deflated at the exact moment that a moving line of earthquakes traveled between them? To answer this question, scientists used deep learning systems such as PhaseNet to examine the enormous amount of seismic data. These machine learning programs detected and precisely located more than 25,000 earthquakes. Each earthquake acted like a tiny underground stress meter. Every tremor revealed how the stress field inside the crust was changing and breaking in response to the pressure of moving magma. The resulting high-resolution earthquake catalog showed that the magma was not rising vertically toward the surface to produce an immediate eruption. Instead, it was moving sideways through the upper crust at a depth of approximately 10 kilometers. A hidden underground highway of liquid rock was forming beneath the Aegean Sea. Scientists combined the INSAR measurements with GPS observations and pressure data from the seafloor. These different datasets were then analyzed together using a mathematical model. The results suggested that approximately 310 million cubic meters of magma had moved out of a reservoir in the middle crust beneath Columbbo. This magma supplied the rapidly expanding underground dike. The evidence revealed that Santorini and Columbbo were not fully independent volcanic systems. They were hydraulically connected. When pressure changed beneath one volcano, the other responded. This behavior exposed an enormous interconnected plumbing system that geologists had never observed so clearly before. To understand why this underground connection exists, we must travel backwards into the deep geological history of the southern Aegean Sea. The ancient population of volcanic centers in this region has been active for more than 650,000 years. The modern islands of Santorini are only the latest features within a much larger and older volcanic region. This region is known as the Cristiana Santorini Columbbo volcanic field. Throughout its long history, the volcanic field has produced more than 100 explosive eruptions. These eruptions repeatedly destroyed, reshaped, and rebuilt the landscape. The prehistoric inhabitants of Santorini, then known as Thera, lived in close contact with this restless geological environment. Around 1620 BCE, the island supported a thriving Bronze Age society centered on the settlement of Akrotiri. Akrotiri was a remarkably advanced city. It contained multi-story stone buildings, elaborate wall paintings, carefully designed streets, and a sophisticated plumbing system. But far beneath this prosperous society, an enormous volume of magma was silently accumulating inside a shallow underground chamber. When the volcanic system finally ruptured, it produced the Minoan eruption, one of the largest volcanic events in recorded human history. The eruption released approximately 60 cubic kilometers of volcanic material. A towering column of ash rose into the atmosphere, while powerful tsunamis struck coastlines across the eastern Mediterranean. As magma escaped from below, the central section of the island collapsed into the emptied underground chamber. This collapse created the enormous water-filled caldera that defines Santorini today. Akrotiri was buried beneath thick layers of volcanic ash. The ash preserved its buildings, streets, artwork, and household objects like a geological time capsule. Centuries later, in the year 1650, the submarine Volcano Columbbo revealed its destructive power. The eruption occurred almost entirely underwater, but it eventually broke through the sea surface. Deadly volcanic gases spread across Santorini, killing approximately 70 people and thousands of animals. The eruption also generated a powerful tsunami that struck the neighboring islands of Ios, Sikinos, and Amorgos. These historical disasters reveal an important truth. The ancestry of these volcanoes is shaped by repeated, high-volume movements of magma. The earthquake crisis of 2025 was therefore not necessarily an isolated or random event. It was another episode in a long-running geological process. The ancient volcanic structures beneath the Aegean remain active. They are still moving, still breathing, and still capable of transferring enormous volumes of molten rock beneath the sea. The mechanism behind the 2025 crisis was not a simple one-way movement of magma. The high-resolution earthquake data revealed that the sideways migration of the dike behaved like a rebounding pump. It moved through the crust in a series of waves and pulses. The magma did not flow smoothly through a permanently open underground tunnel. Instead, it advanced through highly pressurized bursts. As magma was forced out of the deep reservoir beneath Columbbo, it encountered a resistant barrier of rock approximately 43 kilometers from its starting point. The magma could not immediately break through. Pressure began building behind the barrier, bending and stressing the surrounding rock. This produced an intense and concentrated swarm of earthquakes. Then, on February 10, 2025, a powerful new surge of magma arrived from deeper inside the Earth. This fresh injection created enough pressure to break through the underground barrier. The seismic front suddenly jumped forward. The magma then migrated northeastward at speeds greater than 0.4 kilometers per hour. This pulsing, wave-like behavior has important consequences for our understanding of magma movement beneath volcanic regions around the world. As the pressure front moved forward, it opened fresh fractures inside the crust. But when the local pressure decreased, the surrounding rock contracted again. This contraction forced some of the magma to rebound and collect in deeper storage zones. The repeated back-and-forth movement created a complicated environment in which different types of magma could meet and mix. Studies of rocks produced by Columbbo's eruption in 1650 show that its explosive rhyolitic magma was probably activated by a rapid injection of hot, primitive mafic magma from the mantle. This hotter magma entered a colder and shallower reservoir, disturbing the existing material and helping to trigger an explosive eruption. The lateral dike observed in 2025 may represent a modern example of this process. By traveling horizontally between the reservoirs associated with Santorini and Columbbo, migrating magma can interact with chemically different magma stored at various depths. This mixing can increase pressure, release gases, and potentially act as a trigger for future explosive eruptions. The horizontal conduit may therefore function as a giant underground mixing zone, blending the geological DNA of two neighboring volcanoes. Why did the magma choose this particular path? Why did it move almost 30 kilometers toward the northeast instead of rising directly to the surface beneath Santorini? The answer appears to lie in a geographic secret buried deep beneath the seafloor. It is a zone of inherited structural weakness created millions of years ago. The southern Aegean Sea is crossed by an enormous network of tectonic faults. These faults were created by the regional stretching of the crust as the African plate moved beneath the Eurasian plate. One of the most important structures is the Amorgous Fault. This fault produced the devastating magnitude 7.7 earthquake of 1956, one of the most powerful European earthquakes of the 20th century. For decades, geologists believe that the Amorgous Fault ended far to the northeast of Santorini. But during a marine research expedition in 2025, scientists aboard the German research vessel Maria S. Marion used multi-channel reflection seismic equipment to examine the sediment layers beneath the seafloor. The instruments sent sound waves deep into the earth and recorded the returning reflections. This allowed researchers to construct images of geological structures hidden beneath layers of marine sediment. They discovered a previously unknown continuation of the Amorgous Fault. The buried fault extended southwestward along the Anhydros ridge, linking the Amorgous tectonic region with the Columbbo volcanic system. This continuation was hidden beneath thick layers of sediment. It could not be seen on ordinary maps of the seafloor. The seismic images showed that the hidden structure formed a sediment-filled crustal graben. A graben is a block of crust that has dropped downward between two normal faults. This structure may have opened approximately 700 to 800,000 years ago, around the period of an ancient volcanic event known as the Archeos eruption. The old graben is closely aligned with the modern direction of regional tectonic stretching. When magma became pressurized beneath Columbbo in January 2025, it did not need to break through completely fresh and solid rock. Instead, it exploited this ancient zone of weakness. The direction of the 2025 dike matched the buried crustal graben almost perfectly. The old fault system acted like a natural guide, creating a path of least resistance for the magma. The geographic secret of the Anhydros ridge therefore controlled the direction of the underground intrusion. This discovery shows how ancient tectonic structures can continue to influence volcanic dangers in the modern world. To map the hidden magmatic system all the way down toward the boundary of the Earth's mantle, geophysicists had to read the geological DNA of the crust. They used an advanced technique called PMP seismic tomography. This technique works like a planetary-scale medical scan. It uses direct and reflected compressional waves, known as P waves, to produce a detailed three-dimensional image of seismic velocity beneath the volcanic field. Seismic waves travel at different speeds through different types of material. They generally move quickly through cold and solid rock. They slow down when passing through hotter, fractured, porous, or partially molten regions. By measuring these differences, scientists can identify structures that cannot be observed directly. The resulting images revealed a complicated system extending deep into the crust. Beneath Santorini, at depths of approximately 15 to 27 kilometers, scientists identified an enormous high-velocity region known as Anomaly H2. This high-velocity body is interpreted as a mature accumulation of mafic and ultramafic cumulates. These are dense, iron-rich mineral crystals left behind when primitive magma cools and begins to solidify. The dense body acts like a massive geological barrier. It may prevent magma from rising directly from the mantle into the shallow reservoirs beneath Santorini. Because the upward route is blocked, rising magma is forced to move around the edges of the high-velocity structure. This observation led to an even more remarkable discovery. Scientists identified a major low-velocity region at a depth of approximately 11 to 13 kilometers. It was positioned east of Santorini and south of Columbbo. This structure, known as Anomaly L4, appears to contain warm, porous rock filled with an interconnected network of liquid melt. Researchers estimate that the region may contain between 5 and 14% partial melt. This deep storage zone may act as the shared magmatic heart of the entire volcanic field. Separate underground pathways appear to rise from this central region. These pathways supply the distinct shallow reservoirs beneath Santorini and Columbbo. Although the magma inside the two volcanoes can develop different chemical characteristics, both systems may draw material from this broad midcrustal source. The lateral intrusion of 2025 appears to have begun near the edges of this shared magmatic heart. The evidence suggests that Santorini and Columbbo may function like different arteries connected to the same deep geological pulse. The discovery of a horizontal magmatic connection changes how we understand the relationship between human society and the restless Earth. Santorini is not merely a geological laboratory. It is one of the world's most famous tourist destinations. Millions of visitors travel there every year to experience its whitewashed villages, volcanic beaches, dramatic cliffs, and sunset views. The earthquake crisis of 2025 revealed the vulnerability of this heavily visited but geographically isolated island. During the height of the crisis in February, constant shaking created widespread public alarm. Local authorities introduced strict precautionary measures to protect people and infrastructure. Because large volumes of moving water can place additional stress on buildings during earthquakes, hotels and residents were ordered to drain swimming pools. Access to dangerous areas near the caldera cliffs was restricted because repeated shaking had increased the possibility of rockfalls and landslides. Local residents and officials patrolled vulnerable paths to prevent tourists from approaching unstable cliff edges to take photographs. The Greek government also announced emergency funding for the construction of a new evacuation route in the southern part of the island. Officials recognized that Santorini's narrow and winding roads could become serious bottlenecks during a major natural disaster. Seismologists worked under enormous pressure. An incorrect interpretation of the earthquake swarm could have serious consequences. A needless evacuation could damage the island's economy and create unnecessary fear. But underestimating the crisis could leave thousands of people exposed to a sudden volcanic eruption, tsunami, or powerful earthquake. Ultimately, satellite measurements, seafloor observations, and deep learning earthquake analysis indicated that the migrating magma did not have enough buoyancy to break through the seafloor. The earthquake crisis gradually weakened without producing an eruption. But the geological lesson remains. Santorini's modern buildings, roads, hotels, and communities sit above an active and connected magmatic system. Future volcanic risk assessments cannot treat Santorini and Columbbo as completely isolated structures. A change in pressure beneath one volcano may produce a rapid response beneath the other. Understanding this relationship is essential for protecting the people who live in and visit this volcanic paradise. The story of the Santorini Crisis of 2025 is more than a geological puzzle. It is a reminder of humanity's deep connection to the dynamic planet we call home. The white cliffs, blue waters, volcanic beaches, and fertile soils of the Aegean have attracted human communities for thousands of years. But these beautiful landscapes are the direct products of an active subterranean engine. By listening to the signals produced by more than 28,000 earthquakes, scientists revealed a hidden dimension of the world beneath the Mediterranean. Machine learning systems, satellites, GPS instruments, and seafloor sensors allowed researchers to observe magma moving through the crust almost in real time. The evidence showed that the apparently isolated volcanoes presented in traditional textbooks may actually form part of a much larger network. Santorini and Columbbo appear to belong to a connected family of volcanic giants sharing the same deep geological pulse. The magma intrusion of 2025 did not produce an eruption, but it revealed an underground structural blueprint that has changed our understanding of volcanic hazards in the southern Aegean. Neighboring volcanoes may not always behave as separate systems. Pressure released beneath one can influence movement beneath another. Ancient faults can direct magma over long distances. Deep reservoirs can supply several volcanic centers through different pathways. For the residents of Santorini and for communities living near volcanic arcs around the world, this discovery provides an important path forward. It shows that modern technology, combined with a detailed understanding of geological history, can help identify the early warning signs of volcanic unrest. Scientists can map the hidden pathways of magma before it reaches the surface. Authorities can improve evacuation plans, strengthen infrastructure, and develop monitoring systems that consider entire volcanic networks rather than isolated mountains. Beneath the calm, sunlit waters of the Mediterranean, the Earth's hidden heart continues to beat. Its movement is usually silent and invisible, but every earthquake, every change in the ground, and every pulse of magma carries information. We live on a planet that is active, changing, and alive. Our future may depend on how carefully we learn to listen to what it is telling us. Despite the remarkable discoveries made during the 2025 crisis, the deep interior of the southern Aegean still contains several important mysteries. Scientists remain divided over critical features of the Santorini-Columbbo system. These disagreements reveal the limitations of present-day monitoring technology. The first major mystery is a blank region beneath Santorini's caldera. Because of the arrangement of seismic instruments used during earlier scientific experiments, relatively few seismic waves cross the middle crust directly beneath the center of Santorini. This produced a large gap in the underground images at depths between approximately 8 and 15 kilometers. Scientists cannot yet determine whether Santorini contains its own independent mid-crustal magma storage zone. It is also possible that Santorini depends heavily on horizontal transport from the larger shared reservoir located farther east. The second unresolved question concerns the ultimate origin of the magma. The deformation and earthquake evidence from 2025 strongly suggests that Santorini and Columbbo are hydraulically connected within the middle crust. However, geochemical studies of their erupted material continue to indicate different mantle sources. The lava from each volcano contains distinct isotopic signatures. How can two volcanoes receive magma from different mantle sources while also sharing part of the same underground plumbing network? One possibility is that mantle-derived magma changes rapidly as it rises through the lower crust. The melt may interact with older crystals, partially solidified magma, and surrounding rock. These reactions could greatly alter its chemical composition and hide evidence of a shared deeper source. Another possibility is that the connection between Santorini and Columbbo is temporary. The systems may normally operate independently, but become linked during periods of unusually strong tectonic stretching. Under extreme pressure, fractures may open between otherwise separate conduits, creating a short-lived hydraulic connection. Solving these mysteries will require more detailed investigations. Scientists may need deep drilling projects, denser networks of ocean-bottom seismometers, improved satellite monitoring, and advanced computer models. These models must be able to simulate the movement of magma, crystals, water, and volcanic gases through complicated networks of fractured rock. Until that work is completed, the full structure beneath Santorini will remain partly hidden.